Hi, so in this video, I want to go over really like the last definition that we have in terms of how we describe different acids and bases. As a reminder, we've kind of been focused on primarily Arrhenius acids and bases and like Chem 161, and then more in this chapter, the Bronsted-Lowry definition of acids and bases. Here we'll take a look at the very last definition, which are Lewis acids and bases, and just see maybe how there may be some crossover, but also some distinctions between the two. So as a reminder, Bronsted-Lowry defines acids and bases as basically this movement of protons, right? Whether a proton is being donated by an acid or accepted by a base, right? It's the proton that is like the main star of our Bronsted-Lowry definition. Lewis acids and bases, however, focus on electron. I think of electrons as kind of like the opposite of a proton in a way, right? In terms of like charge and things. And so when it comes to like how the electrons are moving, that also gets flipped in our definition. So in the Lewis definition, we define an acid as an electron acceptor. A base then is an electron donor. And so again, here we kind of see this distinction between Bronsted-Lowry focusing on protons being donated or accepted. Lewis does the same thing, but in terms of electrons. One of my like silly mnemonics that I use to remember the different definitions and which applies for a Lewis acid, because it starts with L, I think of L electrons, and acid starts with AC, so acceptor. So I use Lewis acid is an electron acceptor as kind of my primary mnemonic device, and then everything else just kind of like branches out from there. So if a Lewis acid is an electron acceptor, that means then a Lewis base is an electron donor. If a Lewis acid is an electron acceptor, a Bronsted-Lowry acid is a proton donor. So right, both the charge and the giving or taking, that flips as well. Just helpful to have these little tricks and things. But again, based off of this definition, we can see maybe some crossover in terms of like what we were already defining as an acid or a base. For instance, if we consider like when water behaves as a Bronsted-Lowry base, right? Water will accept a proton and become H3O+. When it accepts that proton, what the water is really doing is it's taking a lone pair of the oxygen and it's making a bond with it. So it's taking electron and it's giving those electrons away to a hydrogen so that it can make that H3O+. So the electron donor aspect of Lewis bases is really in perfect agreement with Bronsted-Lowry bases as proton acceptors. It's kind of implied that when you gain a proton, right, that needs to be formed through some kind of bond. And so the electrons that are in that bond, those come from the base itself, right? The base has the electrons, it mates the bond with the proton, and so then that's how we get that basic definition. For acids, however, it's going to change our definition of what an acid looks like a lot. It aligns pretty consistently with certain types of acids. For instance, metal cations acting as an acid, as we saw earlier in the chapter, right? When you have like a metal cation in water, it will become hydrated by the water, and then those water molecules could potentially lose a proton that way. Under this Lewis definition, right, basically when you have like a positively charged cation, that kind of opens it up to accept electrons, right? The positive can be balanced out by the negative electrons, and so the two kind of go hand in hand. It also makes sense when we think about how certain covalent species are acidic by nature. So I don't know how far you went into this in Chem 162, but some of the different like periodic table trends that we looked at involving like metals versus nonmetals. For nonmetal oxides, when those dissolve in water, they tend to be acidic. But if you think about like what a nonmetal oxide may be, for instance, like CO2, right, there's no hydrogen on CO2. So how can it behave as an acid? It can't necessarily by the just proton donor definition. But in terms of a Lewis acid, right, CO2 does have that electron accepting behavior. I draw this out right here as this reaction of carbon dioxide reacting with water, where the water has electrons to donate from the oxygen. That then forms a bond with the CO2, right? So here the CO2 is accepting electrons from the water molecule, and then it mates, as a result, carbonic acid, or H2CO3, right? So that's shown right here on how that CO2 maybe on its own doesn't look like an acid, but once it dissolves in water, it does in fact make an acid. That's because the CO2 itself is acidic by nature, right? It is accepting electrons as is defined by this Lewis definition. Now, to be honest, with the Lewis definition of acids and bases, it can be pretty difficult to just like look at a chemical formula and know whether it's an acid or a base. It's more helpful to draw out the Lewis structure. It's the same Lewis, right? He's obsessed with this stuff. But so to draw out the Lewis structure, you can see then maybe how bonds are being broken or formed, right? How a lone pair can be donated to another atom to make a bond then. So right, when we do have a Lewis acid base reaction, generally what we're looking for is for one of our reactants to have a lone pair on it somewhere. That lone pair is going to make then a bond to the other reactant and then give us just one whole thing. That whole thing we'll refer to as the adduct, right? It's basically adding the acid and base together and making now just like one compound. As an example right here, I have a reaction of dimethyl ether and aluminum chloride. When these two bond, the oxygen of the dimethyl ether, because it has lone pairs, right, it's going to make a bond with the aluminum and then give us this big monstrosity adduct as our product there. And so generalizing these types of Lewis acid-base reactions is really tricky. It's very hard to know exactly how the bonds are going to be formed. That's more something that you would probably learn in like organic chemistry, if anything. But as far as like looking at an overall reaction, right, you can kind of identify what the acid or base is based off of, again, this movement of electrons and just the availability of lone pairs to then form bonds. So let's look at a couple of examples just to kind of help reason through these different Lewis acid-base reactions. Here I have a reaction of boron trifluoride reacting with ammonia to form BF3NH3. I don't know the name for that. It doesn't matter. But so with this reaction, right, I want to know here which of these chemicals is the Lewis acid. Now again, on its face, it may not be super obvious which one is which. So I would suggest probably drawing out the Lewis structures of these different substances, at least definitely of the reactants. That may give you some insight as to which one may be the electron acceptor and which one may be the electron donor. But so probably go ahead and pause here, draw out the Lewis structures of our different chemicals, and see how that electron movement is occurring. All right, so hopefully you got some review in on Lewis structures and drawing out our different covalent species. What you should see from the Lewis structures of, let's say, BF3 and NH3 is that they look pretty similar. They've got like that first atom in the center, right? So boron as the center of BF3, nitrogen as the center of NH3, and then they're each going to have single bonds to each of the other atoms. So just a single bond to each fluorine for boron, a single bond to each hydrogen for nitrogen. Now the difference between these two structures is when we think about how many electrons we need overall in the molecule and how many electrons are basically favored by different elements and different atoms. So for instance, in BF3, there should be a total of 24 valence electrons on that entire structure. And so what that means then is that once we have all of our fluorines up to an octet and with a single bond, boron itself is one of those chemicals that prefers not to have an octet. It can have full 8 electrons around it, but boron, usually we see it in molecules as just 6 electrons. So with those 3 single bonds to the fluorines, boron's satisfied. There's no lone pairs on boron itself. In the NH3, however, because that has a total of 8 valence electrons, basically all 8 of them need to be on nitrogen. So you've got your 3 bonds to the hydrogens and then a lone pair on nitrogen. It's that lone pair that's going to be very crucial for helping us understand which of our reactants is an acid and which is a base. So right, because the BF3 does not have a lone pair and NH3 does, that suggests that NH3 is the electron donor. That's again the base under this definition. So that means then that BF3 is the Lewis acid here. As another example, I have here the reaction of hydroxide and aluminum hydroxide producing some complex ion called AlOH4-. Now this reaction also is an acid-base reaction, even though it doesn't necessarily maybe look like our previous definitions of acids and bases reacting together. But right for this, I want us to also again consider maybe what the Lewis acid would be for this particular substance. So again here, it's a little difficult to just say right off the bat, maybe which is the acid and which is the base. You're just looking at their chemical formulas. It's not totally clear which of these substances really has, say, lone pairs to donate. But if we draw out the Lewis structure, we can see that hydroxide itself has 3 lone pairs on the oxygen. The aluminum in aluminum hydroxide, that has no lone pairs around it. This is very similar to the aluminum chloride in the previous slide. And so the hydroxide seems like a much better electron donor overall because it has all of these lone pairs around it. And so I would guess then that the AlOH3 is our Lewis acid, right? It is the electron acceptor because the OH- is working as a Lewis base. Again, if we're not like totally sure about whether we have an acid or a base, a Lewis base is much easier to identify based off of it having lone pairs. Also, in these two examples, the bases that we used, NH3 and OH-, those are bases from our other examples too. Like ammonia is like our go-to weak base. Hydroxide is the thing that all bases make, and so those look pretty basic to me as well. The other stuff then must be the acid. But so again, that goes over the Lewis definition of acids and bases. Remember that kind of the focus of the Lewis definition is on electrons, whereas the Bronsted-Lowry definition was on protons. Please let me know if you have any questions, and I'm always happy to help. Bye.